Welcome to a journey through deep time, where we explore one of the most transformative climatic events in Earth's history. Today, we're diving into the Carnian Pluvial episode, a phenomenon that sounds like it could be a footnote in geological history, but in reality, it fundamentally reshaped the entire planet and determined which life forms would rise to dominance for the next 165 million years. This is the story of 2 million years of relentless rain. This is the story of ecosystems collapsing under the weight of endless moisture. This is the story of extinction, adaptation, and the improbable rise of a group of animals so small and insignificant that nobody could have predicted they would rule the world. This is the story of how dinosaurs came to be, born not from strength, but from the ability to survive when the world fell apart. If you're watching this video right now, please let us know in the comments where you are in the world and what time you're watching this history video. We would love to hear from you. And if you haven't already, be sure to subscribe to the channel for more deep dives into Earth's most fascinating prehistoric moments. Now, let's begin our descent into the ancient world of the late Triassic. Part 1, The World Before the Rain. To understand the significance of the Carnian Pluvial episode, we must first understand what the world looked like before the rains came. We need to travel back approximately 235 million years, to a time when the Earth was profoundly different from the world we know today. The continents were arranged in a single massive supercontinent called Pangaea, a landmass so enormous that it stretched from pole to pole, covering nearly 40% of the planet's surface. Imagine standing on the shore of this ancient world. The air around you would feel thick and heavy, carrying the scent of unfamiliar vegetation. The sky above would present a different color than the one we see today, tinted by an atmosphere with different chemical compositions. The sun would seem brighter in some ways, yet filtered through a haze created by ongoing volcanic activity. The sound of the world would be alien to modern ears. No bird songs, no insect choruses as we know them, no mammalian calls. Instead, there would be the rustle of primitive plants, the footfalls of enormous creatures, and the occasional roars and hisses of reptiles that dominated every landscape. The Triassic period had already endured for approximately 37 million years by the time we're examining. It was a world recovering from catastrophe. The most catastrophic extinction event in Earth's history, known as the Permian-Triassic extinction or the Great Dying, had occurred roughly 50 million years earlier. That apocalyptic event had eliminated approximately 96% of all marine species and 70% of all vertebrate families. The Triassic was essentially a world of survivors, where life was gradually rebuilding, diversifying, and reestablishing complex ecosystems after nearly being erased entirely. In this recovered world, the landscape was dominated by reptiles, not dinosaurs, not yet. Instead, the world was ruled by a variety of other reptilian groups that had successfully navigated the Permian extinction and flourished in the Triassic world. These animals were perfectly adapted to the conditions of their time, and they occupied nearly every ecological niche available. One of the most dominant groups during this period was the synapsids, though by the time of the Carnian stage of the Triassic, they were a shadow of what they had once been. The synapsids had ruled the world during the Permian period. They included the famous saber-toothed predators and the hulking herbivorous dicynodonts. By the Carnian stage, the synapsids had been reduced to relatively small, marginal creatures that scurried about in the shadows of more dominant reptiles. However, the dicynodonts, those peculiar herbivores with their distinctive pair of tusks, were still present in some ecosystems, still managing to survive and reproduce, still filling important ecological roles. The dicynodonts were absolutely fascinating creatures. These were stocky, barrel-bodied animals that ranged from the size of a large rat to creatures as massive as a hippopotamus. Their most distinctive feature was the presence of a pair of tusks protruding from their upper jaws, along with a beak-like structure that they used for feeding on the plants that dominated Triassic landscapes. They had powerful limbs positioned somewhat beneath their bodies, giving them a gait that was more efficient than many of their reptilian cousins. Some dicynodonts were solitary creatures, while others may have been social, possibly gathering in herds to migrate or forage. They had successfully survived the Permian extinction, and they had thrived during the early and middle portions of the Triassic period. But the dicynodonts were not alone in their dominance. Sharing the Triassic world with them was another group of reptiles called the archosaurs. The archosaurs are crucial to our story because they represented the lineage that would eventually give rise to crocodiles, pterosaurs, and dinosaurs. During the Carnian stage, the archosaurs were diversifying rapidly. Some were aquatic hunters dwelling in rivers and lakes. Others were terrestrial predators, medium-sized to large carnivorous reptiles that stalked the lands in search of prey. Among these archosaurs were creatures called pseudosuchians and other basal archosaurs. These were not the famous predatory dinosaurs that would come to dominate in later periods, but rather more primitive archosaurs that were nonetheless successful hunters and scavengers. They were built for predation, with sharp teeth, powerful jaws, and muscular bodies designed for quick acceleration and pursuit of prey. Many of these archosaurs had powerful hind limbs and smaller forelimbs, a body structure that would be refined and perfected in the dinosaurs that came later. The vegetation of the Triassic world was fundamentally different from what would come to dominate after the Cretaceous. There were no flowering plants during this period. Instead, the world's flora consisted of ferns, conifers, cycads, ginkgos, and various other gymnosperms. These plants formed vast forests that stretched across the supercontinent of Pangaea, creating complex habitats that supported the diverse animal life. The forests were not lush and green in the way that modern tropical rainforests are, but rather had a different character, sparser in some areas, denser in others, but fundamentally structured around the reproductive and growth strategies of non-flowering plants. The climate of the pre-Carnian Triassic was generally warm and arid, with significant seasonal variations in many regions. The interior of Pangaea, particularly the vast regions far from any ocean, was essentially desert-like in character. Temperature variations between seasons could be dramatic, and precipitation was unevenly distributed. Some areas near coastlines and in lower latitudes received adequate moisture, but much of the interior continent was dry, sometimes extremely dry. This created a world of dramatic contrasts, oases of relatively lush vegetation surrounding water sources, transitioning into semi-arid scrublands, which in turn gave way to true deserts in the most interior regions. The oceans during this pre-Carnian period were dominated by various groups of marine reptiles and fish. There were ichthyosaurs, sleek, dolphin-like reptiles that had adapted perfectly to aquatic life. There were plesiosaurs beginning to emerge, though they were not yet the dominant marine predators they would become in later periods. There were various fish species, including ancient sharks and other predatory fish that occupied the higher trophic levels in marine ecosystems. Despite the successful diversification and adaptation of all these life forms, there was no indication that massive change was coming. The ecosystems appeared stable. The dominant groups, the dicynodonts, the various archosaurs, the other reptiles that filled different ecological roles, all seemed well established and successful. Natural selection had honed them to fit perfectly into their respective niches. The world had achieved what appeared to be ecological equilibrium, but this apparent stability was an illusion created by the short timescale of ecological observation. The forces that would transform the world were already building beneath the surface of the planet, in the vast chambers of the mantle where material circulated in tremendous convection currents. Massive plumes of hot rock were rising toward the crust, carrying with them the potential energy that would soon be released in one of the most significant volcanic episodes of the Phanerozoic Eon. The animals of the Triassic had no way of knowing what was coming. They could not sense the tremendous pressure building beneath their feet. They could not predict that their world was about to be subjected to a 2-million-year assault of rain and climatic instability that would shake the foundations of their ecosystems. For them, the future must have seemed secure, the present stable, the world as reliable as it had always been. But reliable worlds are rare in Earth's history, and this one was about to be proven as transient as all the others. Part 2, the trigger volcanic catastrophe. The Carnian Pluvial episode did not arise spontaneously. It was triggered by a cause, a specific set of processes that set in motion the chain of events that would reshape the biosphere. That cause was volcanic activity on a truly massive scale. The volcanic activity that triggered the Carnian Pluvial episode was not a single massive eruption, though volcanic episodes can certainly be dramatic and sudden. Rather, it was an extended period of intense volcanism, a phase during which the Earth's crust was subjected to multiple eruptions across a broad geographic area. This volcanism was caused by the movement of tectonic plates and the rise of massive plumes of hot material from deep within the Earth's mantle. The specific region where much of this volcanic activity was concentrated was located in what is now the western part of modern North America and Central America. This region, during the Carnian stage of the Triassic, was positioned along an active volcanic arc where tectonic plates were colliding and subducting beneath the continental crust. The subduction process, where one plate slides beneath another, creates conditions of extreme heat and pressure that can trigger magmatism and volcanic activity. The magma that formed from this process was buoyant, less dense than the surrounding crustal rock. This magma rose through the crust, reaching the surface in locations separated by tens or even hundreds of kilometers. When the magma reached the surface, it erupted explosively, ejecting vast quantities of volcanic material into the atmosphere. The volcanic products included ash, pumice, and various gaseous compounds that would have profound effects on the planet's climate and chemistry. One of the most important volcanic gases released during these eruptions was sulfur dioxide. Sulfur dioxide is a colorless gas with a pungent odor that forms when sulfur-bearing minerals in the magma are heated and broken down during eruption. When sulfur dioxide is released into the atmosphere, it can react with water vapor and other atmospheric compounds to form sulfuric acid aerosols. These aerosols are minute droplets suspended in the atmosphere that have remarkable effects on planetary climate. When sulfuric acid aerosols are present in high concentrations in the stratosphere, they reflect incoming solar radiation back to space. This reflection of sunlight reduces the amount of solar energy reaching the Earth's surface, which can lead to cooling of the lower atmosphere and surface. This is a well-documented phenomenon that has been observed in historical times whenever major volcanic eruptions have occurred. The eruption of Mount Tambora in 1815 released enough volcanic material to cause a measurable reduction in global temperatures and led to what is often called the year without a summer in the northern hemisphere. The eruption of Mount Pinatubo in 1991 had similar effects on a smaller scale, but the volcanic eruptions that triggered the Carnian Pluvial episode were releasing much more than just sulfur dioxide and ash. They were also releasing carbon dioxide, a greenhouse gas that has the opposite effect of sulfuric acid aerosols. While sulfuric acid aerosols reflect sunlight and cool the climate, carbon dioxide traps heat by preventing it from radiating away from the Earth's surface into space. This trapping of heat, the greenhouse effect, leads to warming of the climate. During the Carnian, these two competing effects would have created a complex climate system, responding to multiple forcing factors. In the short term, the immediate effect of the massive volcanic eruptions would have been cooling caused by the reflection of sunlight by volcanic aerosols. This cooling would have been temporary, lasting only a few years to perhaps a few decades, depending on the size and composition of the eruptions. As the aerosols gradually settled out of the atmosphere and were removed by precipitation and other processes, the short-term cooling effect would fade. But the carbon dioxide released during these eruptions would remain in the atmosphere for much longer, centuries to millennia. The carbon dioxide would accumulate in the atmosphere, gradually increasing the greenhouse effect and leading to warming of the climate. This warming would have been gradual but relentless, building over time as more and more carbon dioxide accumulated from the continuing volcanic eruptions. The volcanic activity itself was not continuous in the sense of being one long eruption. Rather, there were multiple episodes of eruptions separated by periods of relative quiescence. This pattern of episodic eruption is characteristic of volcanic arcs and hotspots. The multiple eruptions would have released additional pulses of carbon dioxide into the atmosphere, each pulse adding to the accumulated greenhouse effect. As the climate warmed due to the accumulating carbon dioxide, other changes would have begun to occur in the climate system. The warming would have increased evaporation from the oceans. When water evaporates from the ocean's surface, it carries heat energy with it. This water vapor enters the atmosphere and, like carbon dioxide, is a greenhouse gas that traps heat. The increase in atmospheric water vapor would have amplified the warming effect, creating a positive feedback loop where warming led to more evaporation, which led to more warming. The increased water vapor in the atmosphere would also have led to increased precipitation. When water vapor cools in the atmosphere, it condenses into liquid droplets that form clouds. If the cooling is sufficient, these water droplets will fall as precipitation. The increased atmospheric water vapor from ocean evaporation would have provided more moisture available for precipitation, and the warming of the climate would have altered atmospheric circulation patterns in ways that would have concentrated this precipitation in certain regions. The volcanic gases released during the eruptions would also have had direct chemical effects on the atmosphere and climate system beyond just their effects on radiation. Volcanic eruptions release not just carbon dioxide and sulfur dioxide, but also nitrogen oxides, hydrogen chloride, and various other compounds. These compounds can participate in atmospheric chemistry reactions that create or destroy ozone, affect the acidity of precipitation, and influenced the lifetime of methane and other greenhouse gases in the atmosphere. The combination of all these factors, the release of carbon dioxide and other greenhouse gases, the increase in atmospheric water vapor, the changes in atmospheric circulation patterns, and the direct chemical effects of volcanic products, created a powerful forcing of the climate system toward a warmer, wetter state. The climate did not shift immediately from arid to wet. Rather, there was a gradual transition as the atmospheric composition changed and the climate system responded. But the response of the climate system to these forcings was not simply a linear change from one state to another. The climate system is capable of complex, nonlinear responses where small changes in forcing can lead to large changes in climate state. The warming trend and increasing atmospheric water vapor created conditions favorable for a reorganization of global atmospheric circulation patterns. The key to understanding how this led to the 2-million-year period of near-constant rainfall lies in understanding how atmospheric circulation works. The Earth's atmosphere is in constant motion, driven by differential heating from the sun and the rotation of the planet. Solar radiation is most intense at the equator and least intense at the poles. This differential heating drives the formation of large-scale circulation cells, the Hadley cells in tropical regions, the Ferrel cells in mid-latitudes, and the polar cells at high latitudes. In a normal climate, these circulation cells are characterized by specific patterns of rising and sinking air. In the tropics, air rises at the equator and sinks at approximately 30 degrees latitude. In these regions of sinking air, the air warms, which increases its capacity to hold water vapor. This means that in these regions of sinking air, there is less precipitation and more evaporation. These are the latitudes where most of the world's major deserts are found: the Sahara, the Arabian Desert, the Australian outback, and the deserts of the southwestern United States. As the climate warmed and the atmospheric water vapor increased during the Carnian, the balance between rising and sinking air shifted. The increased convection in the tropics, driven by the warming surface and the increased latent heat in water vapor, intensified the rising branch of the Hadley circulation. This intensified rising air created regions of stronger convergence at the equator, where air masses collided and were forced to rise. The stronger rising air carried more moisture-laden air into the upper atmosphere. When this moisture-laden air reached the upper atmosphere and cooled, it released its moisture as precipitation. But the effects of the changes in atmospheric circulation did not stop at the equator. The increased intensity of tropical convection and the changes in the Hadley circulation affected the mid-latitude Ferrel cells as well. The jet streams, narrow bands of strong winds in the upper atmosphere that drive much of the day-to-day weather in mid-latitudes, shifted in position and intensity. The result of all these changes in atmospheric circulation was that the pattern of rainfall across the planet shifted dramatically. Regions that had been arid or semi-arid began to receive significant rainfall. Regions that had been wet became even wetter. The pattern of rainfall became less seasonal and more consistent throughout the year. In many regions, the rainfall became truly relentless, month after month, year after year, of persistent precipitation with little respite. The specific pattern of rainfall during the Carnian Pluvial episode varied regionally, but the overall trend was toward increased moisture availability. Paleoclimatic records, reconstructed from geological evidence such as paleosol characteristics, sedimentological patterns, and fossil assemblages, indicate that many regions of Pangaea that had previously been dominated by arid or semi-arid conditions began to experience humid, wet conditions. The shift was not instantaneous. It likely took place over thousands to tens of thousands of years as the climate system gradually reorganized in response to the increasing greenhouse forcing. For the animals and plants that had adapted to the previous arid or semi-arid conditions, this shift would have been profoundly challenging. Evolution operates by natural selection, acting on heritable variation within populations. If the environment changes very gradually, populations can evolve in response through the process of directional selection, where individuals with traits favorable for the new conditions are more likely to survive and reproduce. However, if the environment changes more rapidly than evolutionary change can occur, populations face the prospect of extinction. The rate of environmental change during the Carnian Pluvial episode was likely rapid enough to exceed the rate at which many established populations could evolve in response. But before we examine the ecological collapse that resulted, we must first understand more about the mechanism by which volcanic activity could have maintained the wet climate for such an extended period. Part 3. Maintaining the deluge, the 2-million-year reign. the duration of the Carnian Pluvial episode was remarkable. Not just for days or weeks, not for years or decades, but for approximately 2 million years, the climate system remained locked in a warm, wet state. Understanding how this extended climate state could have been maintained requires us to examine the concept of climate feedback loops and the mechanisms by which a climate perturbation can persist for an extended duration. When the volcanic eruptions released carbon dioxide into the atmosphere, they created a perturbation to the climate system, a forcing that pushed the system away from its previous equilibrium state. In the absence of any feedback mechanisms, the climate system would gradually return to its previous state as the carbon dioxide was removed from the atmosphere through various processes. Carbon dioxide is removed from the atmosphere primarily through the weathering of rocks, a process where atmospheric carbon dioxide reacts with minerals in rocks and sediments to form new minerals and soluble compounds that are carried away by water. The weathering of rocks is a slow process, operating over timescales of hundreds of thousands to millions of years. This means that carbon dioxide released by volcanic activity persists in the atmosphere for a very long time, long enough to significantly alter the climate system, and long enough for the climate system to respond through the operation of various feedback mechanisms. One critical feedback mechanism during the Carnian Pluvial episode was related to the hydrological cycle, the circulation of water between the oceans, atmosphere, and land. The initial warming from the volcanic carbon dioxide increased evaporation from the oceans. This water vapor entered the atmosphere and acted as a greenhouse gas, amplifying the initial warming. The increased water vapor also led to increased precipitation over land and over the oceans. Over land, this increased precipitation had the effect of accelerating the weathering of rocks. Chemical weathering, the process where water and acids derived from the atmosphere and soil react with minerals in rocks, is accelerated by increased moisture. When precipitation is abundant, water infiltrates the soil and rock, creating conditions favorable for chemical reactions between water and minerals. These reactions consume carbon dioxide from the atmosphere as it is incorporated into secondary minerals and dissolved as carbonate and bicarbonate ions carried by water into rivers and ultimately into the oceans. The acceleration of chemical weathering would have served to remove carbon dioxide from the atmosphere. This might seem like a negative feedback, a process that would limit the warming and potentially restore the climate to its previous state. However, the geological and paleoclimatic evidence suggests that the rate of volcanic carbon dioxide release during the Carnian was sufficient to offset the increased rate of carbon dioxide removal through weathering, at least for the duration of the volcanic episode. This balance between volcanic carbon dioxide input and weathering-based carbon dioxide removal is delicate. If volcanic emissions exceed removal through weathering, carbon dioxide accumulates and climate warms. If weathering removal exceeds volcanic input, carbon dioxide decreases and climate cools. The persistence of the warm, wet climate for 2 million years suggests that the volcanic emissions were sufficient to maintain a positive carbon dioxide balance during this entire period. The volcanic activity itself was likely episodic rather than continuous. However, the cumulative effect of multiple volcanic episodes over the 2 million year Carnian Pluvial episode would have been to maintain elevated atmospheric carbon dioxide levels. Each new episode of volcanism would have added additional carbon dioxide to the atmosphere, compensating for the removal through weathering and keeping the overall level of atmospheric carbon dioxide high. The extended warm climate would also have had secondary effects that maintained the wet conditions. The warmer ocean would have had different circulation patterns than a cooler ocean. Ocean circulation is driven by density differences created by differences in temperature and salinity. A warmer ocean would have different density gradients and therefore different circulation patterns. These changes in ocean circulation would affect how heat is transported from equatorial to polar regions and would affect upwelling patterns that bring nutrient-rich deep water to the surface. The warmer ocean would also have increased the rate of evaporation, supplying more water vapor to the atmosphere. The increased atmospheric water vapor would have intensified the hydrological cycle and would have led to more precipitation in many regions. Additionally, the warmer atmosphere would have had greater latent heat content because warm air can hold more water vapor than cool air. This greater latent heat content would have intensified convection in the tropics, leading to stronger updrafts and more intense rainfall in tropical regions. Another important consideration is the effect of the persistent rain on the landscape itself. 2 million years of abundant precipitation would have had profound effects on the physical structure of the landscape, the composition of soils, and the types of ecosystems that could be supported. The persistent wetness would have led to the formation of extensive wetland ecosystems, swamps, marshes, and wet forests. These ecosystems would have had different vegetation than the arid and semi-arid ecosystems that had preceded them. The vegetation that colonized these newly wet landscapes would have been different in composition from the vegetation of the pre-Carnian world. While conifers, cycads, and other gymnosperms would have continued to be important, the specific species composition would have shifted toward plants adapted to wet, possibly waterlogged conditions. Ferns, which prefer moist environments, would have become more abundant and diverse. The landscape would have transformed into one dominated by lush vegetation capable of thriving in high moisture conditions. As the vegetation changed, the feedback effects on the climate system would have continued. Vegetation plays a role in the water cycle through the process of evapotranspiration, the process where water is evaporated from soil surfaces and from plant leaves. The new vegetation adapted to the wet conditions would have had high evapotranspiration rates, returning water that had fallen as precipitation back to the atmosphere as water vapor. This water vapor would have condensed into new clouds and fallen as precipitation, maintaining the cycle. The new vegetation would also have affected albedo, the fraction of incoming solar radiation reflected by the Earth's surface. Vegetation-covered surfaces generally have lower albedo than bare rock or sand, meaning they absorb more solar radiation. The greater absorption of solar radiation would have contributed to maintaining the warm climate. The extensive wet forests that developed during the Carnian would also have affected the atmospheric circulation through the release of volatile organic compounds, organic molecules that evaporate from plant leaves and other surfaces. These volatile organic compounds can participate in atmospheric chemistry, forming secondary organic aerosols that affect cloud properties and precipitation. The specific effects would depend on the composition of the volatile organic compounds and the atmospheric chemistry, but the general effect would have been to enhance cloud formation and precipitation. All of these feedback mechanisms, the release of water vapor from evaporation and evapotranspiration, the acceleration of chemical weathering, the changes in ocean circulation, the changes in vegetation, and the effects of vegetation on albedo and atmospheric chemistry, would have acted together to maintain the warm, wet climate for the 2-million-year duration of the Carnian Pluvial episode. The persistence of the volcanic activity during this period was crucial. If volcanic emissions had ceased, the increased rate of carbon dioxide removal through weathering would eventually have restored the atmosphere to lower carbon dioxide levels, and the climate would have cooled and dried. The fact that the warm, wet climate persisted for 2 million years indicates that volcanic emissions, though likely episodic in nature, were sufficient throughout this period to maintain atmospheric carbon dioxide at elevated levels. The specific volcanism responsible for the Carnian Pluvial episode has been identified in geological records from the western part of North America, particularly in regions of Nevada and California, and in regions of Central America. The volcanic rocks produced during this episode have been dated using radiometric dating techniques, and the dates indicate a sustained period of volcanism lasting approximately 2 million years, spanning much of the Carnian stage of the Triassic period. Part 4: The ecological response when WRLDS collapse. As the climate gradually shifted from warm and arid to warm and wet, the established ecosystems of the Carnian Triassic world began to experience stress. For 2 million years, the environmental conditions that had shaped the evolution of the dominant life forms remained in flux. The dicynodonts, which had evolved and diversified under arid and semi-arid conditions, suddenly found themselves in a world of persistent moisture. The archosaurs and other reptiles that had adapted to the old climatic regime also faced pressure to adapt to the new conditions. Initially, the response of organisms to the changing climate was probably individual-level plasticity, the ability of individual organisms to adjust their physiology and behavior in response to changing environmental conditions. Many organisms possess remarkable plasticity, the ability to adjust their body size, development rate, metabolism, and behavior in response to environmental cues. This plasticity allows organisms to survive in conditions somewhat different from those to which their ancestors were adapted. For some organisms, this plasticity was sufficient to allow them to survive the changing climate, but for others, the magnitude of the environmental change exceeded the limits of individual plasticity. At that point, population-level changes began to occur. Populations of organisms that were well adapted to the old conditions began to decline in numbers. Individuals that possessed heritable traits making them slightly better suited to the new conditions were more likely to survive and reproduce, leading to selection for new trait combinations. This process of evolutionary adaptation can occur very rapidly in some cases, particularly in organisms with short generation times and large population sizes. Bacteria and viruses, for example, can evolve in response to new environmental conditions on timescales of days to months. But for large-bodied, long-lived organisms such as dicynodonts and other large reptiles, the generation time is measured in years to decades. This means that evolutionary change in response to environmental change occurs on timescales of hundreds to thousands of years or longer. The 2-million-year duration of the Carnian Pluvial episode might seem like a very long time, and indeed it is on human timescales, but in terms of evolutionary time, it is not necessarily long enough for large-bodied organisms with slow life histories to adapt to the new environmental regime. The dicynodonts, for example, were large animals that probably had long generation times. A female dicynodont probably did not reach sexual maturity until she was several years old, and the gestation period for her offspring was probably several months. The interval between successive offspring probably was several years. This means the generation time for dicynodonts was probably on the order of 5 to 10 years or longer. With generation times measured in years, and with the need for millions of years for significant evolutionary adaptation to occur, the dicynodonts were on a timetable that did not match the pace of environmental change. The populations of dicynodonts that had thrived in the arid Triassic began to decline as the climate became wetter. The specific mechanisms of this decline are not entirely clear from the fossil record, but there are several possibilities. One possibility is that the changing climate affected the types of vegetation that the dicynodonts relied on for food. The dicynodonts were herbivorous animals, and their feeding apparatus, the specialized beak and the teeth adapted for browsing and processing vegetation, had evolved under conditions where specific types of plants were available. As the vegetation composition shifted toward species adapted to wet conditions, the dicynodonts may have found their preferred food plants becoming less abundant. Additionally, the wetter conditions may have had direct physiological effects on the dicynodonts. Many modern reptiles are sensitive to humidity levels, and many have difficulty regulating their body-water balance in very humid conditions. If the dicynodonts were similarly sensitive, the shift to persistently humid conditions may have imposed physiological stress on them, increasing their metabolic costs and reducing their fitness. The waterlogged soils of the wetter climate also may have affected the dicynodonts. These large animals were probably not particularly efficient swimmers or waders. In a landscape that was becoming increasingly wet, with extensive swamps and marshes replacing the dry areas that may have once been passable, the dicynodonts may have found their habitat fragmenting. Populations that were once continuous may have become isolated in the remaining dry areas, reducing genetic diversity and making the populations more vulnerable to local extinction. As the dicynodont populations declined, the ecosystems in which they had played important roles began to change. The dicynodonts, as large herbivores, had exerted significant ecological impacts on their environments. They consumed vast quantities of vegetation, shaping the structure of plant communities through their feeding. They trampled vegetation and soil. They distributed seeds through their feces, affecting plant distribution and diversity. As the populations of dicynodonts declined, these ecosystem shaping effects diminished. The vegetation that the dicynodonts had helped to shape would have responded to the reduction in herbivory pressure. In the absence of large herbivores preventing the growth of certain plant species, the vegetation would have reorganized toward a composition determined more by climate and soil conditions and less by herbivory pressure. The dense, wet-adapted vegetation would have expanded into areas where dicynodont herbivory had previously kept vegetation at lower density. The decline of the dicynodonts also had cascading effects through food webs. Large herbivores like the dicynodonts are prey for predators. The decline of the dicynodonts would have reduced the available prey for predators that had evolved to hunt them. The predators of dicynodonts may have included various archosaurs and other carnivorous reptiles. These predators, suddenly faced with a shortage of their preferred prey, would have had to either adapt to hunting other prey species or decline in population themselves. Some predators would have been more flexible in their diet, capable of shifting to alternative prey species. Other predators would have been more specialized, with feeding apparatus optimized for hunting dicynodonts specifically. These specialized predators would have been more vulnerable to the decline of their preferred prey and would themselves be more likely to decline or go extinct. The overall pattern of extinction was not uniform. Different lineages responded differently to the environmental and ecological changes. Some groups of reptiles, particularly the archosaurs, showed remarkable resilience and even diversification during the Carnian Pluvial episode. Other groups, particularly the dicynodonts and certain archosaurs, showed significant decline and reduced diversity. The specific archosaurs that showed decline during this period included various groups of basal archosaurs and some early crocodile-like archosaurs. These animals, which had been successful predators and scavengers in the pre-Carnian world, found themselves displaced as the climate changed. The reasons for their decline were multiple. As their ecosystems reorganized, their prey base changed. The new vegetation and the wetter conditions created habitats that were less suitable for these animals, and as we shall see, new competitors were rising to take their place. The Carnian Pluvial episode, therefore, was not just a period of climate change. It was a period of ecological reorganization and wholesale replacement of dominant species. The extinction of dicynodonts was particularly significant because these animals had been dominant herbivores for millions of years. Their extinction represented the end of a major group of large vertebrates that had ruled the Triassic landscape. What is particularly remarkable about the extinctions during the Carnian Pluvial episode is that they were not all instantaneous. The fossil record shows that the decline of some groups was gradual, occurring over tens of thousands to hundreds of thousands of years. This indicates that the stresses imposed by the changing climate and ecosystems were significant but not catastrophically sudden. The organisms experienced directional selection, with different heritable traits being favored under the new conditions. Some populations may have been able to evolve enough to persist, at least for a while, but many populations apparently could not evolve rapidly enough or in the right direction to adapt to the relentless changes, and they gradually disappeared. The extinction of the dicynodonts and the decline of many archosaur groups left ecological vacancies, roles in the ecosystem that were no longer being filled because the organisms that had previously filled them were gone. In ecological terms, these vacancies created opportunities for organisms that could adapt to exploit them. This is where our story takes a crucial turn, because there was a group of organisms present in the world during the Carnian that possessed characteristics making them exceptionally well suited to exploit the opportunities created by the ecological disruption. Those organisms were the dinosaurs. Part 5. The unlikely candidates. Dinosaurs before dominance. Before the Carnian Pluvial episode, dinosaurs existed. This fact is crucial to understand. Dinosaurs did not originate during the Carnian Pluvial episode. They had already evolved, already diversified into multiple lineages, and already established themselves in various ecological niches. However, before the Carnian Pluvial episode, dinosaurs were not dominant. They were not the rulers of their world. In fact, dinosaurs were relatively marginal creatures, occupying secondary ecological roles and comprising a small fraction of the total vertebrate diversity. The earliest dinosaurs appeared in the fossil record approximately 230 million years ago, during the early Triassic period, just a few million years after the Permian extinction. These earliest dinosaurs were small animals, probably ranging from 1 meter to 3 meters in total length. They were bipedal, meaning they walked on 2 hind legs, with the forelimbs being smaller and held off the ground. Their bodies were built for speed and agility, with powerful hind limbs and tails that helped with balance. The earliest dinosaurs were not the dominant predators of their world. Instead, the ecological role of top predator was filled by larger archosaurs, particularly the Roysuchians and other predatory archosaurs that were more heavily built and more powerful than the early dinosaurs. The early dinosaurs were probably mid-sized predators, hunting smaller animals such as early mammals, lizards, and various small vertebrates and invertebrates. Over the millions of years between the earliest dinosaurs and the Carnian stage, dinosaurs gradually diversified. Multiple lineages evolved, each adapted to different ecological niches and prey types. By the Carnian stage, dinosaurs included small predatory species, medium-sized predatory species, and a growing diversity of herbivorous species. The herbivorous dinosaurs had evolved specialized teeth and jaws adapted for processing plant material, and many had developed sophisticated digestive systems capable of extracting nutrition from plant material. However, despite this diversification, dinosaurs still occupied a secondary role in Carnian ecosystems. The dominant large herbivores were still the dicynodonts. The dominant predators were still the larger archosaurs. Dinosaurs were present, persistent, and diverse, but they were not the ecosystem engineers, the organisms whose actions most significantly shaped the structure and composition of their ecosystems. What advantages did dinosaurs possess that would later allow them to rise to dominance? The fossil record, combined with modern understanding of physiology and evolutionary biology, suggests that dinosaurs possessed several key characteristics that distinguished them from many of the other reptiles with which they coexisted. First, dinosaurs possessed an active metabolism. This is a controversial topic among paleontologists and physiologists, and there is genuine scientific debate about the precise level of metabolic activity that early dinosaurs possessed. However, the evidence suggests that dinosaurs had metabolic rates higher than typical modern reptiles, but perhaps not as high as modern mammals and birds. This intermediate metabolic level, sometimes called mesothermy or intermediate metabolism, would have provided dinosaurs with advantages in certain environmental conditions. An active metabolism provides an organism with the ability to maintain sustained activity levels. An organism with active metabolism can sustain running speeds and activity levels for longer periods than an organism with lower metabolic rates. This is advantageous for predators because it allows for sustained pursuit of prey. An active metabolism is also advantageous in cool or variable environmental conditions because it allows an organism to maintain a relatively constant body temperature independent of ambient environmental conditions, a process called thermoregulation. During the arid Triassic before the Carnian Pluvial episode, the advantages of active metabolism might have been limited because the warm climate allowed for thermoregulation through behavioral adjustments, basking in the sun to warm up, seeking shade to cool down. But as the climate became persistently wet and cloudy during the Carnian Pluvial episode, the ability to maintain activity level independent of environmental conditions would have become increasingly valuable. Second, dinosaurs possessed rapid growth rates. This is evident from bone histology. The microscopic structure of dinosaur bones reveals growth rings and bone density patterns indicating that dinosaurs grew relatively quickly compared to many other reptiles. A rapid growth rate means that an organism reaches reproductive maturity in a shorter time than organisms with slower growth rates. This is advantageous because it allows for higher population turnover and faster evolutionary response to environmental changes. Populations of organisms with rapid life histories can adapt more quickly to environmental change than populations of organisms with slow life histories because more generations pass in the same amount of time, providing more opportunities for natural selection to act. The rapid growth of dinosaurs was supported by their physiology. Analysis of bone chemistry and the growth patterns visible in bone histology suggest that dinosaurs were capable of sustained growth, growing from hatchling to adult in perhaps 5 to 15 years for most species, depending on body size. This is much faster than would be expected for a typical reptile of the same body size, suggesting that dinosaurs had metabolic capabilities exceeding those of typical modern reptiles. Third, dinosaurs possessed behavioral flexibility. The fossil evidence for behavior is limited, but it includes trackways suggesting group locomotion, bone bed assemblages suggesting herding behavior, and nesting sites suggesting parental care. This behavioral flexibility would have been advantageous in rapidly changing environmental conditions because it allowed for rapid adjustment of behavioral responses to changing circumstances without requiring evolutionary change. A population of dinosaurs could respond to changing environmental conditions by changing their behavior, forming larger or smaller herds, altering migration patterns, shifting foraging behavior much more rapidly than they could through genetic evolution. Fourth, dinosaurs had specialized teeth and jaws adapted for efficient feeding. The herbivorous dinosaurs, in particular, had teeth and jaws shaped for grinding and processing plant material. Some early herbivorous dinosaurs had teeth designed for stripping vegetation, similar to modern iguanas. Later herbivorous dinosaurs developed even more sophisticated dental batteries, arrangements of teeth designed for efficient mastication of plant material. This specialized feeding apparatus would have allowed dinosaurs to process vegetation efficiently and extract nutrition from plant material that other herbivorous animals might have had difficulty processing. The carnivorous dinosaurs, meanwhile, had teeth and claws shaped for predation. Some early carnivorous dinosaurs had sharp, blade-like teeth designed for slicing through flesh. Claw marks on bones of presumed prey animals suggest that dinosaurs were effective predators, capable of using their forelimbs and their sharp claws as weapons. Fifth, dinosaurs possessed an upright posture. Unlike most reptiles, which have limbs sprawling to the sides of their bodies, many dinosaurs had limbs positioned directly beneath their bodies. This posture was particularly pronounced in bipedal dinosaurs, where the hind limbs were directly under the body, allowing for efficient upright walking and running. The upright posture reduced the metabolic cost of locomotion, meaning that dinosaurs could move greater distances using less energy than reptiles with sprawling postures. The upright posture also had other advantages. It allowed for greater speed, because the limbs could move in a more direct, forward-backward plane rather than having to move laterally and then forward. It provided a higher viewing perspective, allowing an animal to see over vegetation and to spot approaching predators or potential prey from greater distances. For predatory dinosaurs, the upright posture allowed for the use of the forelimbs and claws as weapons while running, a capability not available to reptiles with sprawling postures. All of these characteristics, active metabolism, rapid growth, behavioral flexibility, specialized feeding apparatus, and upright posture, would have provided dinosaurs with advantages during the environmental crisis of the Carnian Pluvial episode. But before we examine how these characteristics allowed dinosaurs to exploit the opportunities created by the extinction of dicynodonts and other organisms, we must understand more about the processes through which dinosaurs came to replace the previous dominant organisms. Part 6. The transition, ecological reshuffling, and competitive displacement. The transition from a dicynodont-dominated world to a dinosaur-dominated world was not instantaneous. It occurred gradually over a period of hundreds of thousands to low millions of years. This gradual transition is evident in the fossil record, where successive levels in stratigraphic sequences show gradual changes in the abundance and diversity of different groups. The process of transition involved several stages. In the earliest stage, as environmental conditions began to shift toward wetter conditions, the populations of organisms adapted to arid conditions began to show signs of stress. The dicynodonts, as we have discussed, began to decline. Various archosaurs that were adapted to arid conditions also began to decline. Meanwhile, organisms that were better adapted to wetter conditions began to increase in abundance and diversity. Among the organisms that benefited from the shift to wetter conditions were various groups of archosaurs adapted to aquatic and semi-aquatic lifestyles. Crocodilians, the ancestors of modern crocodiles, were particularly successful during this period. The shift to wetter conditions with more extensive river systems, lakes, and swamps created habitats favorable for crocodilians, which are semi-aquatic predators that hunt in and around water bodies. The crocodilian fossil record shows increased diversity and abundance during the Carnian, particularly during the Carnian Pluvial episode. Dinosaurs also benefited from the shift to wetter conditions, though perhaps not immediately in all cases. Some dinosaur lineages were better adapted to wetter conditions than others. Dinosaurs that had evolved in more tropical or subtropical regions, where more moisture had been available even before the Carnian Pluvial episode, were probably better suited to the increasingly wet conditions than dinosaurs that had evolved in more arid regions. As the arid regions of Pangaea gradually became wetter, some dinosaur lineages would have had to adapt to these changing conditions, while others would have had already suitable physiologies. The specific mechanisms through which dinosaurs came to replace dicynodonts and other declining groups are complex and likely involved multiple processes. One mechanism was competitive displacement, where dinosaurs were more efficient at exploiting available resources than competing organisms. For example, if dinosaurs were capable of processing vegetation more efficiently than dicynodonts in the new, wetter ecosystems, or if dinosaurs were capable of growing faster and reaching reproductive maturity more quickly, dinosaurs might have outcompeted dicynodonts for available resources. The specific mechanisms of competitive displacement would have depended on the exact nature of resource limitation. In some ecosystems, vegetation might have been abundant, but the dicynodonts were limited by the ability to process vegetation efficiently. In such a case, dinosaurs with superior feeding apparatus might have enjoyed competitive advantage. In other ecosystems, space or other resources might have been limiting, in which case dinosaurs with superior competitive abilities for those resources would have had advantage. Another mechanism of dinosaur expansion was niche partitioning and diversification. As niches left empty by the decline of dicynodonts and other groups became available, different dinosaur lineages could evolve specializations for different ecological roles. Some herbivorous dinosaurs evolved toward larger body sizes, filling the role left by the extinction of large dicynodonts. Other dinosaurs specialized on smaller prey or different types of vegetation. This diversification allowed dinosaurs to expand into multiple ecological niches simultaneously. A third mechanism was trophic cascade, indirect effects on populations resulting from changes in the abundance or behavior of other species. As dicynodont populations declined, the abundance of dicynodonts as prey for predators would have declined. Predators that specialized on dicynodonts would have found their food source dwindling. Meanwhile, predatory dinosaurs would have been capable of hunting other prey species that the dicynodont predators might not have been adapted to hunt. As the dicynodont predators declined, predatory dinosaurs would face less competition for available prey. The relative timing of the diversification of different dinosaur groups is important in understanding this transition. Herbivorous dinosaurs appear to have diversified and increased in abundance before the most dramatic declines of dicynodonts. This pattern suggests that herbivorous dinosaurs were initially increasing in response to the changing climate and vegetation, perhaps expanding into newly created habitats of dense, wet vegetation. The increase in herbivorous dinosaurs would have been followed by an increase in predatory dinosaurs, which would have benefited from the increased abundance of dinosaur herbivores as prey. The early herbivorous dinosaurs of the Carnian included prosauropods, medium to large-sized herbivorous dinosaurs with relatively small heads, long necks, and quadrupedal gait. The prosauropods would eventually give rise to the sauropods, the largest land animals ever to exist. During the Carnian, prosauropods were beginning to increase in size and abundance, apparently successfully exploiting the abundant vegetation of the increasingly wet climate. Alongside the prosauropods were various other herbivorous dinosaurs, including ornithischians and other lineages. Some of these early herbivorous dinosaurs were relatively small, perhaps the size of a sheep or goat. Others were larger, comparable in size to the largest dicynodonts. The range of sizes and the diversity of feeding apparatus among herbivorous dinosaurs of the Carnian suggests that they were partitioning food resources among themselves and with other herbivorous animals, each specialized for different types of vegetation or different feeding strategies. The predatory dinosaurs of the Carnian included various theropods, bipedal, predatory dinosaurs with sharp teeth and claws. The theropods ranged from small, swift predators, perhaps 1 to 2 meters in length, to larger hunters approaching or exceeding 5 meters in length. These predatory dinosaurs appear to have been particularly successful during the Carnian Pluvial episode, increasing in abundance and diversity even as the larger archosaurs that had previously filled the role of apex predator were declining. The success of theropod dinosaurs during the Carnian Pluvial episode can be attributed to several factors. The active metabolism and rapid growth of theropods would have allowed them to maintain high activity levels in the cool, wet climate of the Carnian. The efficient, upright posture of theropods would have allowed them to hunt across the wetter landscape without the difficulties that more sprawling reptiles might have experienced. The specialized predatory apparatus of theropods, sharp teeth and claws, would have made them efficient hunters. The theropods were also probably more adaptable in their diet than the larger archosaurs they were replacing. The larger archosaurs were probably specialized for hunting large prey, large dicynodonts, and other large herbivores. As dicynodonts declined, the large prey base that these archosaurs depended on would have declined. Theropod dinosaurs, being smaller and more agile, would have been capable of hunting smaller prey. They could subsist on small herbivorous animals, early mammals, lizards, and other invertebrates that were available in the ecosystems of the Carnian. The competitive interactions between theropod dinosaurs and the remaining large predatory archosaurs would have been complex. In some regions, theropods may have directly competed with archosaurs for the same prey species. In such competition, theropods might have had advantages because of their superior speed and agility, allowing them to capture prey more efficiently. Theropods might also have been able to survive on a broader diet than archosaurs, allowing them to persist in regions where prey availability was fluctuating due to environmental instability. In other regions, theropods and archosaurs might have partitioned prey resources, with theropods specializing on smaller prey and archosaurs specializing on larger prey. As the Carnian Pluvial episode progressed and dicynodonts and other large animals became less abundant, the archosaurs that depended on large prey would have had less available food, while theropods that could subsist on smaller prey would have had continued access to food. Conclusion of Part 1. The stage is set by the end of the first part of our journey through the Carnian Pluvial episode. We have established the foundation for understanding one of the most transformative events in Earth's history. We have seen how a stable, dicynodont-dominated world of the early Carnian Triassic was fundamentally disrupted by massive volcanic activity that altered the planet's climate and chemistry. We have examined how the release of carbon dioxide and other volcanic gases created a self-reinforcing system of warming and increasing moisture availability. We have traced the mechanisms through which this extended period of warm, wet conditions persisted for approximately 2 million years, maintained by continuing volcanic activity and positive feedback mechanisms within the climate and biosphere systems. We have documented the ecological consequences of this environmental upheaval. The dicynodonts, those remarkable tusked herbivores that had dominated the Triassic landscape, began to decline as their ecosystems reorganized around the new climatic regime. Other groups of animals adapted to arid conditions also faced severe stress. The established ecological hierarchy began to crumble as the conditions on which it was based shifted inexorably toward a new state. And we have introduced the organisms that would come to exploit the vacancies created by this ecological disruption, the dinosaurs. These small to medium-sized reptiles, with their active metabolism, rapid growth, behavioral flexibility, specialized feeding apparatus, and upright posture, possessed characteristics that would prove to be remarkably well suited to the new climatic and ecological conditions. In the second part of our examination of the Carnian Pluvial episode, we will explore in greater detail how dinosaurs came to exploit these opportunities. We will examine the specific mechanisms through which dinosaurs diversified and expanded, coming to fill the ecological roles left vacant by the extinction of dicynodonts and the decline of other groups. We will explore how a group of animals that had been marginal and secondary in their ecological importance came to become the dominant large vertebrates on land, a position they would maintain for the next 165 million years. But the story is not finished yet. There is much more to understand about the Carnian Pluvial episode and its consequences for the history of life on Earth. The transformation of Earth's biosphere was neither simple nor instantaneous, but rather a complex process involving countless interactions between organisms, ecosystems, and the physical environment. The Carnian Pluvial episode reminds us of a fundamental truth about our planet, that apparent stability is often an illusion created by the short timescale of human observation. The stable world of the pre-Carnian Triassic changed fundamentally and irrevocably within just 2 million years. The organisms that had ruled that world were displaced by newcomers. The landscape was transformed. The very fabric of ecological relationships was rewoven. This same principle applies to our modern world. The stability that we perceive in our environment, the consistency of climate, the predictability of seasons, the abundance of familiar plant and animal species, is also an illusion created by the short timescale of human experience. Over geological time, the planet's climate shifts, ecosystems reorganize, and dominant species are replaced by newcomers. Understanding the Carnian Pluvial episode helps us appreciate the dynamic nature of our planet and the possibility of rapid and extensive change in response to environmental disruption. Thank you for joining us on this journey into deep time. In Part 2, we will continue our exploration of the Carnian Pluvial episode, examining in greater detail how dinosaurs rose to prominence and how this ancient climate event set the stage for the age of dinosaurs that followed. Until then, please leave your thoughts in the comments below, and don't forget to subscribe to the channel for future explorations of Earth's most fascinating prehistoric events. Welcome back to our continued exploration of the Carnian Pluvial episode. In Part 1, we established how massive volcanic activity triggered 2 million years of relentless rainfall, and how this environmental catastrophe devastated the established ecosystems of the Triassic world. We witnessed the decline of the dicynodonts, those remarkable tusked herbivores that had ruled for millions of years, and we introduced the dinosaurs, a group of organisms that possessed characteristics perfectly suited to surviving the chaos and exploiting the opportunities that emerged. Now, in Part 2, we will dive deeper into the mechanisms of ecological transformation. We will examine how dinosaurs diversified and expanded their ecological roles. We will explore the specific adaptations that made dinosaurs so successful in the new climate. We will trace the detailed progression of the extinction of established groups and the rise of dinosaurs, using the fossil record to reconstruct a narrative of biological transformation occurring across 2 million years of environmental instability. This is a story of innovation and adaptation, of ecological opportunity and evolutionary response, of how a global climate catastrophe created the conditions for the rise of the most dominant group of land animals in Earth's history. Let's continue our journey into the ancient world of the late Triassic. Part 7, the fossil record reading the story in stone. To understand the transition from a dicynodont-dominated world to a dinosaur-dominated world, we must turn to the fossil record. The rocks deposited during the Carnian stage preserve evidence of the biological communities that inhabited the Earth during this time, and by examining these rocks and the fossils they contain, we can reconstruct the sequence of ecological changes that occurred during the Carnian Pluvial episode. The fossil record is not a complete record of life in the past. It is instead a selective sample, biased in ways that we must understand and account for. Organisms are preserved as fossils only under specific conditions. Generally, rapid burial in sediments under anoxic conditions prevents decomposition and allows the hard parts of organisms to be preserved. Soft tissues are rarely preserved unless there are exceptional circumstances. Small animals and organisms with fragile skeletal structures are less likely to be preserved than large animals with robust skeletal structures. Organisms that lived in environments conducive to rapid sedimentation, rivers, deltas, lakes, are more likely to be preserved than organisms that lived in well-drained uplands where rapid sedimentation did not occur. Despite these biases, the fossil record provides a remarkably informative window into past life. By examining the composition of fossil assemblages from successive layers of rock, we can track changes in the types of organisms present through time. By counting the number of bones of different taxa in fossil assemblages, we can estimate relative abundance. By examining the size and developmental stage of fossils, we can understand something about the population structure of extinct species. The Carnian stage rocks have been studied extensively from localities around the world. Some of the most informative localities are in what is now the southwestern United States, particularly in Nevada and Arizona. Other important localities are in Argentina, Brazil, Germany, Scotland, and various other locations. The fossils from these localities paint a consistent picture of ecological change during the Carnian. In the early Carnian, before the onset of the Carnian Pluvial episode, the fossil record shows a world dominated by large dicynodonts and large predatory archosaurs. Dinosaurs are present in the fossil record, but they are relatively rare and typically represented by small to medium-sized individuals. The dicynodonts are abundant, represented by multiple species and individuals of various sizes, suggesting healthy populations that varied in age and size structure as would be expected in a thriving ecosystem. As we move forward in time through the early Carnian and into the middle Carnian, the period of most intense rainfall and climatic instability, the composition of fossil assemblages changes markedly. The dicynodonts become progressively less abundant. The number of individual dicynodont fossils per unit volume of rock decreases. The number of dicynodont species represented also decreases, suggesting that some lineages went extinct while others persisted, but at reduced population levels. Simultaneously, the abundance of dinosaur fossils increases. Dinosaurs that were rare in early Carnian assemblages become more common in middle Carnian assemblages. The diversity of dinosaurs also increases, with new forms appearing that are not present in earlier assemblages. The size distribution of dinosaurs changes as well, with larger dinosaurs becoming increasingly common. The large predatory archosaurs that had been common in early Carnian assemblages also show a pattern of decline during the middle and late Carnian. Some lineages of large predatory archosaurs completely disappear from the fossil record. Others persist, but at reduced abundance. Meanwhile, crocodilians, the ancestors of modern crocodiles, increase in abundance and diversity, suggesting that these semi-aquatic predators were well suited to the wetter conditions. One of the most striking patterns in the fossil record of the Carnian is the turnover of herbivorous animals. In the early Carnian, large dicynodonts dominate the herbivore fossil record. By the middle to late Carnian, large dinosaurs are the dominant herbivores. This turnover occurred gradually, with a period during the middle Carnian when both dicynodonts and dinosaurs were present, and both contributing significantly to the herbivore fauna. The pattern of turnover suggests that the replacement of dicynodonts by dinosaurs was not a sudden catastrophic event, but rather a gradual process of competitive displacement and ecological reorganization. Had the replacement been sudden, had all dicynodonts died simultaneously, we might expect to see a sharp boundary in the fossil record between assemblages with dicynodonts and assemblages without them. Instead, what we see is a gradual transition with a period of overlap during which both groups were present. This gradual pattern of turnover is consistent with the idea that the Carnian Pluvial episode imposed stress on dicynodont populations, causing them to decline gradually as conditions worsened. As dicynodont populations declined, the competitive pressure from dinosaurs would have become more significant. Dinosaurs, better adapted to the new conditions, would have gradually expanded into ecological space left vacant by declining dicynodonts. Eventually, as dicynodont populations became small enough, random extinction events or environmental fluctuations would have eliminated the remaining populations. The fossil record also provides evidence of the specific mechanisms through which dinosaurs came to dominate. By examining the teeth and skeletal structures of dinosaurs from successive time periods within the Carnian, paleontologists can observe evolutionary changes in response to the changing environment. For example, some dinosaur lineages show a trend toward increased body size through the Carnian, suggesting that natural selection favored larger body size as the climate changed. Other lineages show changes in tooth shape or jaw structure, suggesting that dietary preferences or feeding strategies were shifting in response to changes in available vegetation. The fossil record of plants during the Carnian also provides important context for understanding the faunal changes. Pollen and spore records, evidence of plant reproduction preserved in rocks, show shifts in plant community composition during the Carnian Pluvial episode. Early Carnian plant assemblages are dominated by conifers and cycads adapted to drier conditions. Middle to late Carnian plant assemblages show increases in ferns and other plants adapted to wetter conditions. This shift in plant community composition would have had direct effects on herbivorous animals, changing the types of vegetation available to eat and likely affecting the abundance of different vegetation types. The shift from a conifer-dominated flora to a flora with higher proportions of ferns would have had significant effects on herbivorous dinosaurs. Ferns are generally less nutritious than conifers, requiring herbivores to process larger volumes of vegetation to obtain the same amount of nutrition. This would have favored herbivorous dinosaurs that were efficient at processing vegetation, dinosaurs with specialized teeth and jaws, dinosaurs with large digestive systems, or dinosaurs with behavioral adaptations, allowing them to select the most nutritious parts of plants. The dicynodonts, with their specialized beaks and teeth adapted for processing certain types of plants, might have been less efficient at feeding on the fern-dominated vegetation of the wet Carnian climate. This dietary inflexibility might have contributed to their decline as the plant community shifted. In contrast, dinosaurs that were more dietary flexible or that had feeding apparatus capable of efficiently processing fern-dominated vegetation would have had competitive advantage. Part 8. Dinosaur evolution during the Carnian adaptation and diversification. The dinosaurs that came to dominance during the Carnian Pluvial episode did not arrive in the world fully formed and perfectly adapted. Rather, they diversified and evolved in response to the changing environmental conditions, and their evolutionary trajectory during the Carnian Pluvial episode shaped the characteristics that would define dinosaurs for the remainder of the Mesozoic era. The herbivorous dinosaurs of the Carnian included several distinct groups, each with different evolutionary histories and adaptations. The prosauropods were among the most successful herbivorous dinosaurs of the Carnian. These were medium to large-sized dinosaurs with long necks, relatively small heads, and 4 legs that supported massive bodies. The prosauropods were likely browsers, reaching up into vegetation that other herbivores could not access. The long neck would have allowed them to feed on vegetation at height while keeping their massive bodies at a safe distance from potential predators. The prosauropods show a pattern of increasing body size through the Carnian. Early Carnian prosauropods were relatively modest in size, perhaps 5 to 8 meters in length. By the late Carnian, some prosauropod species had grown to lengths of 10 meters or more. This trend toward larger body size during the Carnian is particularly significant because it suggests that the environmental conditions of the Carnian Pluvial episode favored large body size in herbivorous dinosaurs. The advantage of large body size in an herbivorous animal is complex. On one hand, larger animals require more food per individual, which could be disadvantageous if food is scarce. On the other hand, larger animals can process vegetation more efficiently because they have larger digestive systems and can afford to process larger volumes of lower quality vegetation. Larger animals are also less vulnerable to predation because predators are less likely to attack prey that is too large to be killed easily. Additionally, larger animals are more efficient at thermoregulation in some conditions because their lower surface area to volume ratio means they lose less heat to the environment. The trend toward larger body size in Carnian prosauropods suggests that the conditions of the Carnian Pluvial episode, wet climate, abundant vegetation, but perhaps lower quality vegetation requiring large digestive systems to process efficiently, favored evolution toward larger body size. The prosauropods would eventually give rise to the sauropods, the largest land animals ever to exist. The transition from prosauropods to sauropods involved continued evolution toward larger body size, further lengthening of the neck, and refinement of the body structure for supporting massive weight. The sauropods would dominate the large herbivore niche for the remainder of the Mesozoic era, but the foundations for their evolution were laid during the Carnian Pluvial episode through the evolution of their prosauropod ancestors. Another important group of herbivorous dinosaurs during the Carnian were the ornithischians. The ornithischians were characterized by a different body plan than the prosauropods. They were typically bipedal or facultative quadrupeds, meaning they could walk on either 2 or 4 legs depending on circumstances. They had smaller body sizes than many prosauropods, though some ornithischians grew to considerable size. They had teeth and jaws specialized for grinding and processing vegetation, different from the more simple leaf-stripping teeth of prosauropods. The ornithischians represent a different evolutionary solution to the problem of being a herbivore. Where prosauropods were large browsers reaching high into vegetation, ornithischians were often smaller and could be either grazers or browsers feeding on lower vegetation. The diversity of ornithischians during the Carnian suggests that they were exploiting different vegetation resources than the prosauropods, partitioning the available herbivore niche. The predatory dinosaurs of the Carnian, the theropods, show different evolutionary patterns than the herbivorous dinosaurs. Rather than showing a clear trend toward increased body size, theropods show diversification into multiple size classes. Small theropods, perhaps 1 to 2 meters in length, were common and apparently successful. Medium-sized theropods, 3 to 4 meters in length, were also present. Larger theropods, approaching 5 meters or more in length, were less common but still present. This diversity of theropod body sizes suggests that theropods were partitioning the predator niche, with different-sized predators hunting different sizes of prey. Small theropods would have hunted small animals, early mammals, small lizards, insects, and other invertebrates. Medium-sized theropods would have hunted animals of medium size, small dinosaurs, other reptiles, and larger invertebrates. Larger theropods would have hunted larger prey, including small to medium-sized herbivorous dinosaurs and other large animals. The theropods show several important evolutionary trends during the Carnian that would be refined in later periods. The teeth of theropods became increasingly specialized for predation, with sharp, recurved, backward-curved edges optimized for cutting flesh. The claws on the hind feet became larger and sharper, suggesting that these were important predatory weapons. The balance of the body became more refined for efficient bipedal locomotion, with the center of gravity shifting to allow for stable upright posture even in running animals. One of the most important evolutionary developments in theropods during the Carnian was the refinement of the forelimbs and claws. Some theropod lineages developed enlarged claws on the hands that would have been useful for grasping prey or for slashing. The development of these killing claws represents a major innovation in predatory apparatus, allowing theropods to become increasingly efficient hunters. All of these evolutionary changes in both herbivorous and predatory dinosaurs during the Carnian Pluvial episode were driven by natural selection, acting on heritable variation within populations. The changing environmental conditions, increased moisture, shifts in vegetation composition, changes in prey and predator availability, created selection pressures that favored certain traits over others. Over many generations, the frequencies of advantageous traits increased within populations, while the frequencies of less advantageous traits decreased. The rapid evolutionary change evident in dinosaur lineages during the Carnian suggests that selection pressures were strong and that there was substantial heritable variation in populations that selection could act upon. The presence of abundant variation is crucial for rapid evolutionary change. If populations had been genetically uniform, they could not have evolved rapidly in response to changing conditions. The genetic variation present in dinosaur populations likely arose through two main processes: mutation and gene flow. Mutations, changes in the DNA sequence caused by copying errors, damage, or other processes, continuously introduce new genetic variation. Gene flow, movement of individuals or their genes between populations, can introduce genetic variation from other populations into a given population. The combination of these two processes would have maintained sufficient genetic variation within dinosaur populations to allow for rapid evolutionary response to selection. Part 9. The Physiology of Success: Why Dinosaurs Thrived. The success of dinosaurs during the Carnian Pluvial episode can be understood not only through ecological competition and evolutionary adaptation, but also through the unique physiological characteristics that dinosaurs possessed. These physiological characteristics gave dinosaurs advantages in the new climate and environmental conditions of the Carnian Pluvial episode. As we discussed in Part 1, dinosaurs possessed an active metabolism. This active metabolism appears to have been maintained through a combination of physiological mechanisms. Dinosaurs had relatively large hearts and efficient respiratory systems compared to typical reptiles. The structure of dinosaur lungs appears to have been more efficient at extracting oxygen from the air than the lungs of typical modern reptiles. Dinosaurs had bone structures indicating substantial vascularization, blood vessels running through and around the bones providing oxygen to bone tissue. The active metabolism of dinosaurs would have allowed them to maintain activity levels that would have been impossible for typical reptiles. In the cool, wet climate of the Carnian Pluvial episode, where cloud cover would have been extensive and sunshine limited, behavioral thermoregulation through basking in the sun would have been difficult. Dinosaurs, with their active metabolic rates allowing thermoregulation through internal heat generation, would have been able to maintain activity level independent of environmental conditions. This advantage would have been particularly important for predatory dinosaurs. The ability to maintain sustained high activity levels would have allowed theropods to pursue prey over long distances and to maintain hunting activity even during cloudy periods when environmental temperatures would have been cool. In contrast, large archosaurs and other reptiles relying primarily on environmental heat for thermoregulation would have had difficulty maintaining the same activity levels during the cool, cloudy periods of the Carnian Pluvial episode. For herbivorous dinosaurs, the active metabolism would have allowed them to maintain activity levels necessary for foraging even in the cool, wet environment. The ability to maintain sustained activity would have allowed them to move through wet landscapes and to search for adequate nutrition without waiting for periods of warmth. The active metabolism would also have required more food intake than a lower metabolism, but the abundant vegetation of the wet Carnian climate would have provided the necessary resources. The rapid growth rates of dinosaurs represented another crucial physiological advantage during the Carnian Pluvial episode. Rapid growth allowed dinosaurs to achieve adult size and reach reproductive maturity in a relatively short time. For large herbivorous dinosaurs, reaching adult size quickly would have meant that individuals could participate in reproduction and pass on their genes to the next generation while still relatively young. In an environment characterized by instability and frequent stress from environmental fluctuations, the ability to reproduce at a young age, and therefore to have multiple generations within a short time period, would have been advantageous. A population with rapid generation times can adapt more quickly to environmental changes through natural selection. If environmental conditions change, selection can act on a population with rapid generation times more effectively because the change in allele frequencies with each generation is larger, and more generations pass in a given time period. The growth mechanisms that allowed dinosaurs to achieve rapid growth appear to have been based on sustained bone deposition and mineral accumulation. The bone histology of dinosaurs, the microscopic structure visible when bones are sectioned and examined under a microscope, reveals growth lines and bone density patterns indicating that dinosaurs deposited bone tissue at substantial rates. This rapid bone deposition would have required substantial mineral intake and dietary resources, but would have allowed for rapid expansion of body size. Another important physiological characteristic of dinosaurs was their efficiency at converting food into body tissue and growth. Metabolism can be measured in terms of metabolic rate, the amount of energy expended per unit time, and in terms of metabolic efficiency, the proportion of energy intake that is converted into growth and reproduction as opposed to being lost as heat. Dinosaurs appear to have had metabolic efficiencies higher than typical reptiles, meaning that a larger proportion of the energy they consumed was converted into growth rather than being expended as heat. This metabolic efficiency would have been advantageous in the environment of the Carnian Pluvial episode. The abundant vegetation would have provided the energy resources necessary to support the growth and reproduction of dinosaurs. The high metabolic efficiency of dinosaurs would have allowed them to convert this abundant vegetation into growth and reproduction more effectively than competitors with lower metabolic efficiency. The behavioral flexibility of dinosaurs also represented an important physiological advantage during the Carnian Pluvial episode, though the mechanisms underlying behavioral flexibility are more difficult to understand from the fossil record. Evidence for dinosaur behavior comes from trackways, nesting sites, bone bed assemblages, and other evidence preserved in rocks. This evidence suggests that some dinosaurs engaged in herd movement, suggesting social behavior and coordinated group locomotion. Some dinosaurs appear to have gathered at nesting sites, suggesting parental care and possibly social reproductive behavior. The ability to engage in complex social behavior would have allowed dinosaurs to respond flexibly to environmental challenges. In an environment characterized by instability, the ability to form groups and coordinate behavior could have allowed dinosaurs to respond more effectively to environmental fluctuations. Herding behavior, for example, could allow animals to respond more quickly to changing environmental conditions by moving as a group to find resources or avoid hazards. The thermoregulatory capabilities of dinosaurs were also likely superior to those of typical reptiles. While dinosaurs were not endothermic, maintaining constant body temperature through metabolic heat generation, in the way that modern mammals and birds are, they were likely capable of maintaining relatively stable body temperatures through a combination of metabolic and behavioral mechanisms. This capability would have been important in the cool, wet, possibly cloudy environment of the Carnian Pluvial episode. The large body sizes of some dinosaurs, particularly the prosauropods, would have conferred thermoregulatory advantages through gigantothermy, the maintenance of relatively stable internal body temperature through the thermal inertia of a large body mass. Large animals have low surface area to volume ratios, meaning they lose heat to the environment more slowly than small animals. This thermal inertia would have allowed large dinosaurs to maintain relatively stable internal temperatures even in an environment with significant temperature fluctuations. Part 10. Ecological restructuring, the reorganization of communities. The transition from a dicynodont-dominated ecosystem to a dinosaur-dominated ecosystem involved not just the replacement of one group of animals by another, but a fundamental reorganization of entire ecological communities. This reorganization involved changes in the abundance and diversity of multiple groups of organisms, changes in the structure of food webs, and changes in the physical structure of habitats. The extinction of large dicynodonts represented the elimination of a major guild of large herbivores. The dicynodonts occupied the ecological role of large browsing herbivores that had shaped vegetation structure through their feeding. As dicynodont populations declined, their role as vegetation shapers was lost, and vegetation structure would have shifted in response to the reduced herbivory pressure. With fewer large herbivores controlling vegetation growth, the vegetation would have responded by growing denser and taller in many areas. The plant communities would have reorganized toward a composition determined more by climate and soil conditions and less by herbivory pressure. This reorganization would have created new habitat structures that would have been advantageous for some organisms and disadvantageous for others. The early dinosaurs that replaced dicynodonts as dominant herbivores did not necessarily fill the ecological roles occupied by dicynodonts identically. While both dicynodonts and early dinosaurs were large herbivores, they likely had different feeding strategies and different impacts on vegetation. The prosauropods, with their long necks and quadrupedal posture, would have fed on vegetation at different heights and in different ways than the dicynodonts. The prosauropods appear to have been specialized for reaching high vegetation, while dicynodonts appear to have been more generalized feeders. This difference in feeding strategy would have meant that the prosauropods would have exerted different selection pressures on vegetation than the dicynodonts had. The prosauropods, by preferentially feeding on high vegetation, would have selected for vegetation with the ability to grow tall and to regrow after being damaged by high browsing. The change in vegetation structure resulting from this shift in herbivore feeding strategy would have had cascading effects throughout the ecosystem. The structure of the predator fauna also underwent significant reorganization during the Carnian Pluvial episode. The large archosaurs that had been the apex predators of early Carnian ecosystems were increasingly replaced by theropod dinosaurs. This shift in apex predator would have had significant effects on ecosystem structure and function. The large archosaurs appear to have been specialized for hunting large prey. Their large size and robust build would have allowed them to subdue large prey items such as large dicynodonts. As dicynodonts declined, the prey base available for these specialized large predators would have diminished, making it increasingly difficult for the large archosaurs to survive. The theropod dinosaurs that replaced them as apex predators appear to have been more generalized and flexible in their diet. Theropods of various sizes could exploit prey of different sizes, from small animals to medium-sized dinosaurs. The flexibility of theropod predators would have allowed them to persist in ecosystems where prey availability was fluctuating due to the environmental instability of the Carnian Pluvial episode. The replacement of large specialized archosaur predators by more generalized theropod predators represents an important ecological transition. In general, in unstable environments, organisms with more generalized niches and more flexible behaviors tend to persist better than organisms with highly specialized niches. The theropods, with their flexible diet and adaptable behavior, would have been better suited to the unstable conditions of the Carnian Pluvial episode than the specialized large archosaurs. The reorganization of predator and herbivore communities would have had effects on populations of smaller vertebrates as well. The early mammals, which had evolved in the Triassic but remained small and relatively uncommon, would have experienced changes in their ecological environment as dinosaurs diversified. With the rise of dinosaurs, the ecological space available to small vertebrates would have shifted. Some niches available to small animals when dinosaurs were rare might have become more competitive as dinosaur diversity increased. However, small animals would also have benefited from some of the changes in ecosystem structure resulting from the transition to dinosaur dominance. The abundant vegetation of the wet Carnian climate would have provided abundant resources for small animals to consume. The insect populations that consumed vegetation would have been abundant and diverse, providing food for insectivorous animals. The reorganization of vegetation structure might have created new microhabitats and refugia where small animals could persist and thrive. The changes in ecosystem structure would also have affected larger arthropods and other invertebrates. The shift from arid to humid conditions would have increased the abundance and diversity of organisms requiring moist conditions. Insects, particularly flying insects that would lay eggs in water, would have thrived in the wet Carnian climate. The diversity and abundance of insects would have provided food sources for insectivorous vertebrates, supporting the populations of small predatory dinosaurs and other insectivorous animals. The reorganization of plant communities during the Carnian Pluvial episode would have had effects on all animals consuming plants or dependent on plants. The shift from conifer-dominated vegetation to vegetation with higher proportions of ferns and other moisture-loving plants would have changed the palatability and nutritional content of available vegetation. Some herbivorous animals would have adapted to consuming the new vegetation types, while others would have found the shift to their diet sources challenging. The aquatic ecosystems of the Carnian Pluvial episode also underwent significant reorganization. The increased rainfall and the resultant changes in hydrology, the distribution and flow of water, would have created more extensive river systems, more stable lake levels, and more extensive wetlands. These increased water bodies would have provided habitat for aquatic animals, particularly reptiles adapted to aquatic or semi-aquatic lifestyles. Crocodilians diversified and increased in abundance during the Carnian Pluvial episode, apparently taking advantage of the expanded aquatic and semi-aquatic habitats. Ichthyosaurs and other marine reptiles also showed diversification and increased abundance. The expansion of aquatic habitats would have created ecological opportunities for aquatic animals to diversify and increase in abundance. The overall pattern of ecosystem reorganization during the Carnian Pluvial episode was one of increasing ecological complexity. The diversification of dinosaurs, the expansion of aquatic animals, the reorganization of plant communities, and the establishment of new ecological relationships created ecosystems with higher species diversity and more complex food webs than the ecosystems of the early Carnian. Part 11, the filtering process, ecological filtering and extinction, the survival and diversification of dinosaurs during the Carnian Pluvial episode, and the extinction of dicynodonts and other groups, can be understood through the concept of ecological filtering. Ecological filtering is the process through which environmental conditions or biological interactions filter the species that can persist in a given environment, allowing some species to persist while others go extinct. The environmental conditions of the Carnian Pluvial episode acted as a powerful filter, selecting for organisms with certain characteristics while selecting against organisms with other characteristics. This filtering process operated at multiple levels, at the level of individual physiological tolerance, at the level of population dynamics, and at the level of ecosystem structure and function. At the individual physiological level, the cool, wet climate of the Carnian Pluvial episode would have created physiological challenges for organisms adapted to warm, arid conditions. Animals adapted to arid conditions might have been prone to overheating in the warm climate, or they might have had difficulty with water balance and osmoregulation in the humid conditions. Animals adapted to arid conditions might also have had difficulty with thermoregulation in the cool periods that might have occurred, particularly if cloud cover prevented behavioral thermoregulation through basking. Dinosaurs, with their active metabolism and efficient thermoregulation, would have been less affected by these physiological challenges. The ability to maintain stable internal temperatures independent of environmental conditions would have allowed dinosaurs to function normally even in the challenging climatic conditions of the Carnian Pluvial episode. At the population dynamics level, the environmental instability of the Carnian Pluvial episode would have created oscillations in population sizes for many species. Species with slow reproduction rates and long generation times would have been particularly vulnerable to population decline during periods when environmental conditions were unfavorable. Large-bodied animals with slow reproduction rates would have had more difficulty recovering from population crashes than small-bodied animals with fast reproduction rates. The dicynodonts, as large animals with presumably slow reproduction rates, would have been particularly vulnerable to this kind of population fluctuation. Once a dicynodont population had crashed due to unfavorable environmental conditions, recovery would have been slow, and the population might have remained at low numbers for an extended period. During this period of low population size, the dicynodont population would have been vulnerable to extinction from random events, disease, drought, or demographic accidents. Dinosaurs, with their faster reproduction rates and faster generation times, would have been better able to recover from population crashes. If environmental conditions improved temporarily, a dinosaur population could increase in numbers relatively quickly, taking advantage of favorable conditions. This ability to respond quickly to favorable environmental conditions would have given dinosaurs a competitive advantage in an unstable environment. At the ecosystem level, the extinction of dicynodonts and other groups and the rise of dinosaurs represented a reorganization of ecosystem structure. As dicynodonts declined, the role of large herbivore was left vacant. Dinosaurs, being present in the ecosystem at the time of dicynodont decline, were available to fill this vacant role. The ecologically flexible nature of dinosaurs would have allowed them to adapt their feeding behavior and ecological niche to exploit the vacant herbivore roles. The concept of ecological filtering helps explain why extinction events often result in rapid diversification of surviving groups. Extinction events eliminate some groups while leaving others intact. The surviving groups then expand into the ecological space left vacant by extinct groups, diversifying rapidly as different lineages adapt to exploit different vacant niches. The Carnian Pluvial episode demonstrates this principle perfectly. As dicynodonts and other large animals went extinct, dinosaurs diversified rapidly, filling the vacant ecological niches. An important aspect of ecological filtering during the Carnian Pluvial episode was the selective advantage of generalization over specialization. The dicynodonts, for example, appear to have been highly specialized feeders, with specialized teeth and jaws adapted for processing specific types of vegetation. When the vegetation composition of the Carnian changed, the specialized feeding apparatus of dicynodonts might have been less effective than the more generalized feeding apparatus of early dinosaurs. Similarly, the large archosaurs that had been apex predators appear to have been specialized for hunting large prey. When the large prey base declined with the extinction of dicynodonts, the specialized predatory apparatus and hunting behavior of large archosaurs would have been less effective. The theropod dinosaurs, with their ability to hunt prey of various sizes and their behavioral flexibility, would have been better able to adapt to the changing prey base. This general principle, that generalists do better than specialists in unstable environments, is well established in ecology. The Carnian Pluvial episode provides a dramatic example of this principle, with specialized groups like the dicynodonts going extinct while more generalized groups like dinosaurs thrived. Another important aspect of ecological filtering during the Carnian Pluvial episode was the selective advantage of organisms capable of rapid growth and reproduction. In a varying, unstable environment, organisms that can reproduce and grow quickly have an advantage because they can take advantage of favorable periods to increase population size rapidly, and they can have more generations pass in a given time period, allowing more opportunities for natural selection to act and for populations to adapt to changing conditions. The dinosaurs, with their rapid growth rates and shorter generation times compared to dicynodonts and large archosaurs, would have had this advantage. The ability to have more generations in the same time period would have allowed dinosaur populations to adapt more rapidly to environmental changes than populations of dicynodonts or large archosaurs. Part 12, the middle Carnian turn over the critical transition, the middle portion of the Carnian Pluvial episode, roughly 230 to 228 million years ago, represents a critical transition in the history of life. During this interval, the extinction of dicynodonts and large archosaurs reached its peak, while the diversification of dinosaurs also accelerated. Paleontologists have identified this interval as particularly important for understanding the transition from a non-dinosaur-dominated world to a dinosaur-dominated world. The specific paleontological evidence for this transition comes from detailed examination of fossil-bearing rock layers from multiple localities around the world. These rock layers, when dated using radiometric techniques and compared to establish their age relationships, show a consistent pattern. Early Carnian rocks contain fossil assemblages dominated by dicynodonts and large archosaurs, with dinosaurs present but relatively rare. Middle Carnian rocks show a transitional composition, with both dicynodonts and dinosaurs present but dinosaurs becoming increasingly common. Late Carnian rocks show fossil assemblages dominated by dinosaurs, with dicynodonts rare or absent. This pattern has been observed in fossil localities from the southwestern United States, from Argentina, from Brazil, and from other regions, suggesting that the transition was not local to a particular region, but was a global phenomenon occurring across multiple continents. The cause of the dramatic turnover during the Middle Carnian is likely related to the intensity of environmental instability during this period. The Middle Carnian corresponds to the period of most intense rainfall during the Carnian Pluvial episode. The climate was likely at its most chaotic during this interval, with extreme swings in moisture availability, possibly including periods of intense rainfall alternating with periods of relative dryness. The vegetation would have been undergoing rapid changes in response to these climatic fluctuations. For organisms adapted to the relatively stable arid climate of the early Carnian, the extreme instability of the Middle Carnian would have been catastrophic. Dicynodont populations, already declining through the early Carnian, would have faced severe stress during the Middle Carnian, with many populations crashing to extinction. The specialized large archosaurs, similarly adapted to the previous climate and now facing an unfamiliar prey base as dicynodonts declined, would also have faced severe stress. In contrast, dinosaurs, with their flexible diets, fast reproduction rates, and adaptable behavior, would have been better positioned to survive the extreme instability of the Middle Carnian. The populations of dinosaurs that had been common in early Carnian ecosystems would have thrived as environmental conditions shifted further toward the warm, wet regime to which they were adapted. The diversification of dinosaurs during the Middle Carnian was not uniform across all dinosaur lineages. Different lineages responded differently to the changing conditions. Some dinosaur lineages went extinct during the Middle Carnian, unable to adapt to the rapidly changing conditions. Other lineages thrived and diversified. Among the most successful dinosaur lineages during the Middle Carnian were the prosauropod herbivores and the small to medium-sized theropod predators. Both of these groups show evidence of rapid diversification during the Middle Carnian, with new species appearing and populations expanding. The prosauropods show a pattern of increasing body size and changing proportions during the Middle Carnian. Some prosauropod lineages show the beginnings of the quadrupedal specialization and massive body size that would characterize the sauropods. The specialization for high browsing and the development of longer necks relative to body size accelerated during the Middle Carnian. The theropods also diversified during the Middle Carnian, with new forms appearing and existing forms becoming more abundant. The size range of theropods expanded, with both larger and smaller forms becoming more common. The predatory apparatus of theropods' teeth, claws, and jaw structure became increasingly specialized during the Middle Carnian, suggesting that theropods were becoming increasingly efficient predators. The Middle Carnian turnover had important consequences for the further evolution of dinosaurs and for the trajectory of life on Earth. The lineages of dinosaurs that diversified and became successful during the Middle Carnian would go on to dominate the rest of the Mesozoic era. The prosauropod lineage that evolved during the Middle Carnian would give rise to the sauropods, which would remain the largest land animals until the end of the Cretaceous. The theropod lineage that diversified during the Middle Carnian would eventually give rise to the birds, which have remained dominant as small flying animals down to the present day. The extinction of dicynodonts and large archosaurs during the Middle Carnian also had important consequences for the further evolution of other groups. The extinction of dicynodonts eliminated a lineage of large herbivorous synapsids that had dominated the landscape for millions of years. The smaller synapsids, the ancestors of mammals, would survive and eventually give rise to modern mammals, but the large synapsid herbivores of the Permian and Triassic were gone. The decline of large archosaurs during the Middle Carnian did not eliminate the entire archosaur lineage. Crocodilians and pterosaurs, both archosaurs, survived and diversified. But the large terrestrial archosaurs that had filled the role of apex predators in early Carnian ecosystems were replaced by theropods. This replacement would have lasting consequences for the evolution of predatory behavior and anatomy in large carnivorous animals. Part 13. The late Carnian whirled a new equilibrium by the end of the Carnian Pluvial episode. Approximately 227 million years ago, the world had fundamentally changed. The 2-million-year period of intense rainfall and climatic instability was ending as volcanic activity waned, and as carbon dioxide removal through weathering began to exceed volcanic carbon dioxide input. The climate was beginning to stabilize into a new equilibrium state. The biosphere that emerged from the Carnian Pluvial episode was profoundly different from the biosphere of the early Carnian. Dinosaurs were now the dominant large vertebrates on land. The dicynodonts that had ruled the early Carnian were extinct. The large archosaurs that had been apex predators were greatly reduced in diversity and abundance. The vegetation had undergone a transition from arid adapted to wet adapted forms, and though this vegetation was beginning to shift back toward drier conditions as climate stabilized, the composition would never return to exactly what it had been before the Carnian Pluvial episode. The late Carnian fossil assemblages reflect this new state. Dinosaurs of various sizes and types are abundant in late Carnian deposits. Prosauropods have grown to impressive sizes, with some individuals reaching lengths of 7 to 8 meters or more. Theropods of various sizes are common, with small predators, medium-sized predators, and large predators all represented. Herbivorous ornithischians are diverse and abundant. The extinction of dicynodonts at the end of or shortly after the Carnian represents one of the most significant extinction events in vertebrate history. A group that had dominated the landscape as the largest herbivores for millions of years had been eliminated. All the lineages of large herbivorous synapsids were gone. In the Permian and early to middle Triassic, the synapsids had been the dominant large vertebrates on land. By the late Carnian, they had been reduced to small, marginal creatures, the ancestors of modern mammals that played only minor roles in ecosystems. The replacement of dicynodonts by dinosaurs as the dominant large herbivores had important implications for the evolutionary trajectory of life on Earth. If dicynodonts had survived the Carnian Pluvial episode and remained the dominant herbivores, the subsequent evolution of large vertebrates might have been very different. The evolution of herbivorous animals might have taken a different trajectory, with dicynodonts continuing to diversify and evolve new forms rather than dinosaurs filling the herbivore roles. Similarly, if the large specialized archosaurs had remained the dominant predators rather than being replaced by theropods, the evolution of large carnivorous animals would have been different. The anatomy and behavior of predatory animals might have evolved differently under the selective pressures operating on archosaurs compared to theropods. The fact that dinosaurs became the dominant large vertebrates during the Carnian Pluvial episode set the stage for the 165 million year reign of dinosaurs that followed. For the remainder of the Mesozoic era, from the end of the Carnian Pluvial episode until the extinction of non-avian dinosaurs 66 million years ago, dinosaurs would be the dominant large vertebrates on land. This 165 million year domination of dinosaurs represents one of the longest and most successful radiations of any group of animals in Earth's history. The success of dinosaurs was built on the foundation of adaptations that had been refined during the Carnian Pluvial episode: the active metabolism, the rapid growth, the behavioral flexibility, the specialized feeding apparatus, and the upright posture. The late Carnian world also saw important developments in other groups of animals. Mammals, which had originated in the Triassic, were still small and relatively rare. The specific characteristics that would eventually allow mammals to dominate after the extinction of non-avian dinosaurs were evolving during the Carnian and immediately after, but these characteristics had not yet reached their full development. Mammals of the late Carnian were small insectivorous animals, occupying the same ecological niches they would continue to occupy for the next 165 million years. Flying reptiles, the pterosaurs, were beginning their own diversification during the late Carnian. Pterosaurs would go on to dominate aerial niches for the remainder of the Mesozoic, competing with early birds and other flying animals for control of airspace. The origins of pterosaurs and the reasons for their success are not yet fully understood, but they may have been related to some of the same characteristics that made dinosaurs successful: rapid growth, active metabolism, and efficient locomotion. Part 14, the climatic recovery, the end of the reign. The Carnian Pluvial episode did not end instantaneously. Rather, it waned gradually as the environmental conditions that had maintained it slowly shifted. The volcanic activity that had triggered the episode and maintained it through carbon dioxide release gradually decreased. The rates of carbon dioxide input from volcanism decreased, while the rates of carbon dioxide removal through weathering remained high. As atmospheric carbon dioxide concentrations began to decline, the greenhouse effect weakened. The climate gradually began to cool and dry. The intense rainfall that had characterized the Middle Carnian began to diminish. The cloudiness that had blocked incoming solar radiation gradually decreased. The humidity of the atmosphere gradually declined. This transition from wet to dry conditions would have created additional environmental stresses on organisms already stressed by the 2 million years of instability. However, by this point, the dicynodonts and large archosaurs had already declined to low numbers or extinction. The organisms that now dominated the landscape, the dinosaurs, had been selected for characteristics that allowed them to thrive in the new conditions, just as they had thrived in the wet conditions of the Carnian Pluvial episode. The shift from wet to dry conditions would have selected for different characteristics than the shift toward wet conditions had. In the drying climate of the late Carnian and post-Carnian world, organisms capable of surviving in arid conditions would have had advantages. This might seem contradictory. Earlier we noted that dinosaurs thrived in the wet Carnian climate, so how could they also thrive in the drying climate? The answer lies in the flexibility of dinosaurs. Dinosaurs as a group were not absolutely dependent on wet conditions. Rather, they were capable of surviving in a range of climatic conditions. Some dinosaur lineages were better adapted to wet conditions, while others were better adapted to arid conditions. As the climate drifted from wet to arid during the late Carnian and the transition to the Norean stage, dinosaur lineages that were adapted to arid conditions would have had advantages. The vegetation of the late Carnian and the Norean would have shifted back toward drier adapted forms as the rainfall diminished. Conifers and other drought-tolerant plants would have increased in abundance, while moisture-loving plants like ferns would have declined. This shift in vegetation composition would have required adjustments in herbivorous dinosaurs, but the flexible feeding apparatus and generalist diet of most dinosaurs would have allowed them to adapt to the new vegetation. The climatic recovery from the Carnian Pluvial episode would have taken thousands to tens of thousands of years. This extended recovery period would have allowed for continued evolution and adaptation of dinosaurs and other organisms to the gradually changing conditions. By the end of the recovery period, the climate of the late Carnian and early Norean would have been different from both the arid pre-Carnian climate and the wet middle Carnian climate. It would have been an intermediate state with seasonal variation in precipitation, but not the extreme wetness of the Carnian Pluvial episode. Part 15, Cascading Consequences: The Long-Term Impacts of the Carnian Pluvial The Carnian Pluvial episode, which lasted approximately 2 million years, had consequences that extended far beyond its duration. The extinction of dicynodonts and the rise of dinosaurs during this episode shaped the subsequent evolution of life on Earth for the remaining 165 million years of the Mesozoic era and beyond. One of the most important long-term consequences was the elimination of large synapsid herbivores from terrestrial ecosystems. The dicynodonts had been the dominant large herbivores of the early Triassic, and their extinction during the Carnian closed off an evolutionary lineage that had been successful for millions of years. The remaining synapsids, the ancestors of mammals, were small and remained small for millions of years to come. The ecological role of large herbivore would be filled by dinosaurs for the rest of the Mesozoic era. This had important consequences for the evolution of herbivory. The anatomy and physiology of herbivorous animals were now shaped by the selective pressures operating on dinosaurs rather than synapsids. Herbivorous dinosaurs evolved very different anatomical solutions to the problems of being a large herbivore than the dicynodonts had employed. Rather than the specialized grinding teeth and beak of dicynodonts, many dinosaurs evolved extensive grinding tooth batteries or simply swallowed stones to grind up vegetation in their gizzards. The digestive systems of dinosaurs evolved to process vegetation differently than the digestive systems of dicynodonts. Another important consequence was the replacement of large archosaur predators by theropod dinosaurs as apex predators. This had important implications for the evolution of predatory behavior and anatomy. The theropods would evolve to become increasingly sophisticated predators, developing larger teeth, sharper claws, more powerful jaws, and increasingly coordinated predatory behavior. Some theropod lineages would eventually evolve to become the most impressive predatory animals ever to exist, the large tyrannosaurs of the late Cretaceous. The extinction of dicynodonts and the rise of dinosaurs also had important implications for the evolution of smaller animals. The diversification of dinosaurs created ecological opportunities for smaller animals to exploit. Some dinosaurs, particularly small omnivorous dinosaurs, may have competed with small mammals and other small animals for resources. However, dinosaurs would never become small enough to completely outcompete all small animals for all resources. Throughout the Mesozoic, small animals, mammals, early lizards, various other vertebrates, continued to persist and evolve in the ecological spaces not occupied by dinosaurs. The rise of dinosaurs also had long-term implications for the evolution of flight. The pterosaurs, which originated during or shortly before the Carnian, would evolve to become the dominant flying vertebrates of the Mesozoic. Later, during the Jurassic, birds would evolve from small theropod dinosaurs and would join pterosaurs in the aerial realm. The competition between pterosaurs and birds for aerial niches would drive innovations in flying apparatus and behavior. Ultimately, birds would outlast pterosaurs, and modern birds are the direct descendants of theropod dinosaurs that originated during the Carnian Pluvial episode or shortly thereafter. The diversification of dinosaurs during the Carnian also set the stage for the evolution of large body sizes that would culminate in the sauropods. The prosauropods that originated during the Carnian would be the ancestors of the sauropods, which would become the largest land animals ever to exist. Some sauropods would eventually reach lengths of up to 30 meters or more and weights exceeding 80 metric tons. The evolution of such enormous body sizes would have important consequences for terrestrial ecosystems throughout the Mesozoic, affecting vegetation structure, nutrient cycling, and the overall structure of ecosystems. Another important long-term consequence of the Carnian Pluvial episode was the establishment of a new baseline for oceanic and atmospheric conditions. The carbon dioxide released by volcanic activity during the Carnian would remain in the atmosphere for an extended period, maintaining elevated atmospheric carbon dioxide levels even after the volcanic activity waned. This elevated carbon dioxide would continue to affect climate for millions of years after the Carnian Pluvial episode ended. The elevated atmospheric carbon dioxide of the post-Carnian world would have had effects on plant evolution. Plants respond to elevated carbon dioxide through changes in stomatal density, the density of pores on leaves used for gas exchange. Plants might also show changes in leaf shape, thickness, or other characteristics in response to elevated carbon dioxide. The evolution of plants during the post-Carnian Mesozoic would have been shaped by the elevated carbon dioxide levels established during and persisting after the Carnian Pluvial episode. The Carnian Pluvial episode also had long-term consequences for ocean chemistry and biology. The increased weathering of rocks during the episode would have increased the input of dissolved nutrients into the oceans. These nutrients would have affected marine primary productivity and would have shaped the evolution of marine ecosystems. The changes in ocean chemistry established during the Carnian Pluvial episode would have persisted for millions of years, affecting marine animal evolution throughout the Mesozoic. Part 16. Understanding Deep Time and Ecological Change. The Carnian Pluvial episode provides us with a window into processes that occur on geological timescales, processes that are difficult for humans to fully appreciate because they occur over millions of years. To understand the Carnian Pluvial episode and its consequences is to understand something fundamental about our planet and the way it changes through time. The first fundamental lesson from the Carnian Pluvial episode is that the apparent stability of our world is often an illusion created by the brief timescale of human observation. The early Carnian world seemed stable, established ecosystems with dominant species seemingly secure in their roles. Yet within 2 million years, those dominant species were gone, their ecosystems restructured beyond recognition, and the world had been fundamentally transformed. A time span of 2 million years is incomprehensibly long from a human perspective. The entire history of human civilization, from the origins of agriculture to the present day, covers only about 10,000 years. The entire evolution of modern humans from our primate ancestors covers only about 6 to 7 million years. 2 million years is a time span that encompasses vast periods of human history, yet it was simply the duration of a single environmental episode in Earth's history. Yet despite the vast timescale, the changes that occurred during the Carnian Pluvial episode were dramatic and consequential. The replacement of one dominant group by another, the extinction of entire lineages, the reorganization of ecosystems, these are not gradual, imperceptible changes. They are dramatic transformations of the biological world. The second fundamental lesson from the Carnian Pluvial episode is that environmental change can be rapid and dramatic on geological timescales. The climate shifted from arid to wet not instantaneously, but within thousands to tens of thousands of years. This is rapid change by geological standards, and the biological consequences of this rapid climate change were equally dramatic. The third lesson is that extinction and diversification are intimately connected. The extinction of dicynodonts and other groups during the Carnian Pluvial episode created ecological opportunities that dinosaurs exploited. Without the extinction, dinosaurs might never have risen to dominance. The diversification of dinosaurs was enabled by the extinction of competing groups. This principle, that extinction creates opportunities for diversification, is fundamental to understanding evolution and ecology. Extinction is not simply a loss, it is also an opening. It is the removal of competitors and the creation of vacant ecological niches that other organisms can exploit. The fourth lesson is the importance of evolutionary potential, the capacity of organisms to evolve in response to changing environmental conditions. Dinosaurs possessed characteristics, rapid growth, active metabolism, behavioral flexibility, adaptable feeding apparatus, that made them capable of evolving rapidly in response to the changing conditions of the Carnian Pluvial episode. Dicynodonts, with their slower growth and reproduction rates and their more specialized feeding apparatus, lacked this evolutionary potential and went extinct. The fifth lesson is the importance of understanding ecological context. Dinosaurs did not simply beat dicynodonts in competition. Rather, the environmental changes of the Carnian Pluvial episode created conditions that favored organisms with dinosaur-like characteristics and disfavored organisms with dicynodont-like characteristics. The success or failure of organisms depends critically on the environment in which they exist and the characteristics they possess relative to that environment. The sixth lesson is about the concept of ecological filtering. The Carnian Pluvial episode filtered the biota, selecting for organisms with characteristics suited to the new environmental regime and selecting against organisms with characteristics suited to the old environmental regime. This filtering process explains the pattern of extinction and survival we observe in the fossil record. Conclusion of Part 2. The world transformed. The Carnian Pluvial episode represents a turning point in Earth's history. The 2 million year period of intense rainfall and climatic instability, triggered by massive volcanic activity, fundamentally restructured the terrestrial biosphere. The world that emerged from the Carnian Pluvial episode was a different place from the world that had entered it. The dicynodonts, those remarkable tusked herbivores that had successfully navigated the Permian extinction and thrived through much of the Triassic, had been eliminated. The large archosaurs that had served as apex predators of early Carnian ecosystems had been displaced. In their place came dinosaurs, a group that had been marginal and insignificant before the Carnian Pluvial episode, but that now had diversified and expanded to become the dominant large vertebrates on land. This transition from a non-dinosaur-dominated world to a dinosaur-dominated world did not occur instantaneously. It was a gradual process occurring over the 2-million-year duration of the Carnian Pluvial episode, with the most dramatic changes occurring during the Middle Carnian, when environmental conditions were most unstable. The dinosaurs that rose to prominence during the Carnian Pluvial episode possessed characteristics that made them exceptionally well suited to surviving and thriving in the new environmental conditions. Their active metabolism allowed them to maintain activity level independent of environmental conditions. Their rapid growth allowed them to reach reproductive maturity quickly and to have more generations passing in a given time period, allowing for rapid evolutionary response to changing environmental conditions. Their behavioral flexibility allowed them to adjust their behavior in response to changing conditions without requiring genetic evolution. Their specialized feeding apparatus allowed them to efficiently extract nutrition from the available vegetation. Their upright posture made them efficient runners and allowed them to inhabit landscapes with complex terrain. All of these characteristics were not new innovations that appeared during the Carnian Pluvial episode. Rather, they were characteristics that had evolved in earlier dinosaurs and that had been present, though perhaps not yet fully realized, before the Carnian Pluvial episode. The Carnian Pluvial episode provided the environmental context in which these characteristics were strongly selected for, and in which dinosaurs with these characteristics could thrive and expand. The diversification of dinosaurs during the Carnian Pluvial episode set the trajectory for the entire rest of the Mesozoic era. The prosauropods that evolved and expanded during the Carnian would give rise to the sauropods, which would become the largest land animals ever to exist. The theropods that diversified during the Carnian would eventually give rise to birds. The ornithischians that appeared during the Carnian would eventually give rise to the elaborate horned and armor-plated dinosaurs of the late Cretaceous. For the next 165 million years after the Carnian Pluvial episode, dinosaurs would remain the dominant large vertebrates on land. This period of dinosaur dominance would witness the evolution of new dinosaur groups, the extinction of old groups, the colonization of new environments, and the development of increasingly sophisticated ecological relationships. But the foundation for all of this was laid during the Carnian Pluvial episode, when dinosaurs rose to prominence and established themselves as the dominant large vertebrates. The Carnian Pluvial episode also had important consequences for other groups of organisms. The extinction of dicynodonts eliminated one lineage of large synapsids, but the smaller synapsids, the ancestors of mammals, survived. These small mammals would continue to evolve and diversify throughout the Mesozoic era, gradually developing the characteristics that would eventually allow mammals to become dominant after the extinction of non-avian dinosaurs 66 million years ago. The origins of modern mammals can be traced back to the Carnian and immediately post-Carnian world, where the selective pressures operating on early mammals were shaping them into the forms they would maintain throughout the Mesozoic. Similarly, the diversification of pterosaurs and the origins of birds, both important groups of flying animals, can be traced to the Carnian and post-Carnian world. The Carnian Pluvial episode, while primarily an event affecting terrestrial ecosystems, had consequences that extended to marine and aerial ecosystems as well, affecting the evolution of all major groups of organisms. The Carnian Pluvial episode stands as one of the most important climatic events in Earth's history. It rivals other major climatic events like the Permian extinction event, the Cretaceous-Paleogene impact event, and others in its consequences for the evolution of life on Earth. Understanding the Carnian Pluvial episode helps us understand how our planet works, how climate change can drive biological change, and how extinction and diversification are intimately connected processes that work together to shape the history of life. As we contemplate the 165 million year reign of dinosaurs that followed the Carnian Pluvial episode, we should remember that this reign would never have occurred without the environmental catastrophe of the Carnian. The dinosaurs that would eventually become the largest and most impressive animals ever to live on land owe their very dominance to their success in surviving and thriving during the environmental upheaval of the Carnian Pluvial episode. Without the Carnian Pluvial episode, the history of life on Earth would have taken a very different path. The Carnian Pluvial episode reminds us that our planet is dynamic and ever-changing. The world that seems stable to us today might be transformed beyond recognition over the course of millions of years. The species that seem dominant today might become extinct. New species might rise to prominence and reshape the ecosystems we take for granted. This is the story written in the rocks, the story of a dynamic planet with a constantly changing biosphere, shaped by the interaction of physical and biological processes operating on geological timescales. The study of the Carnian Pluvial episode provides us with insights into the processes that drive evolution and shape ecosystems. It shows us how climatic change can cause extinction, how extinction creates opportunities for diversification, how organisms with favorable characteristics exploit these opportunities to rise to dominance, and how the biosphere reorganizes itself in response to environmental change. These lessons are not merely of historical interest. They are relevant to our understanding of how our modern world might change in response to future environmental perturbations, whether from volcanic activity, asteroid impacts, changes in solar radiation, or other causes. The Carnian Pluvial episode is a reminder that Earth's biosphere is resilient but also vulnerable, capable of extensive reorganization in response to environmental change, and shaped by processes that operate on timescales that seem incomprehensibly long to human observers, but that are fundamental to understanding our planet's history. Thank you for joining us on this two-part exploration of the Carnian Pluvial episode. We have traced the story from the stable, dicynodont-dominated world of the early Carnian through the environmental catastrophe of the Carnian Pluvial episode, to the emergence of a dinosaur-dominated world that would persist for the remainder of the Mesozoic era. We have examined the mechanisms through which volcanic activity triggered the episode, the ecological consequences of the episode, and the long-term impacts of the episode on the evolution of life on Earth. Please continue to explore the deep history of our planet. Subscribe to the channel for more documentaries exploring Earth's most fascinating prehistoric events. Leave your thoughts and questions in the comments below, and remember that understanding our planet's past is essential for understanding our world today and imagining the possibilities of our planet's future. The Carnian Pluvial episode reminds us that we live on a dynamic planet, shaped by processes operating on geological timescales, where extinction and evolution work together to continuously reshape the biosphere. By understanding this deep history, we gain perspective on our own place in the vast expanse of geological time and appreciation for the remarkable diversity of life that has evolved on our world.